Okay, so for this video, we'll be going through this transfer of thermal energy or thermal processes. As you have done this in Sec 2 already, so we'll just quickly go through some important concepts that you may have forgotten. Okay, so for this chapter, there are only 5 success criteria, and basically it's talking about how thermal energy is being transferred. So we have conduction and convection, and lastly radiation. So for this chapter, usually there's no calculation associated with it, right? So if you know the concept, you will score quite easily. Okay, so success criteria is show an understanding that energy is transferred by heating, okay, from a region of higher temperature to a region of lower temperature until thermal equilibrium is achieved between the two regions. So I believe thermal equilibrium is a new term. Okay, so let's see. Now, all metal contains energy in the internal store. We just did this in a previous chapter, and this is also called internal energy. Now, what is important is that the energy in the internal store is equal to the sum. That means I add up all the potential energy due to the intermolecular forces and the kinetic energy due to the motion of the particles. So you might want to take note that potential energy depends on the distance between particles. Okay, between particles. Okay, and it's the highest in gas. Whereas kinetic energy is due to the temperature. Okay, so it is highest in gas as well. Okay, now energy is transferred from a region of higher temperature to a region of lower temperature until both have the same temperature. And now this is called, and now they are in a state of thermal equilibrium. So you need to memorize this. Thermal equilibrium describes a state, okay, in which two or more objects have the same temperature, okay, and there is no net transfer of energy between them. Okay, so if I have two substances A and B touching each other, okay, so initially maybe 70 degrees, this is 30 degrees, and we know that thermal energy will be transferred from higher to lower temperature. So eventually they may reach something like 54 degrees. This is where they reach thermal equilibrium after some time, okay, and there is no net transfer. No net transfer means like your net force, nothing, no more transfer. But in between, there could be some from A to B, some from B to A, because different areas, different spots may not have the same temperature, right? So, but overall, there is no longer a transfer of thermal energy between them, okay? So energy transfer by heating occurs only when there's a difference in temperature. If there's no difference in temperature, then there's no more energy transfer. Okay, we can look at this example. This is a hot cup of tea. Okay, and the initial temperature is 80 degrees. Okay, final temperature is 30 degrees. So the hot tea was at a higher temperature than the surrounding air. Therefore, energy was transferred from the hot tea to the surrounding air. Okay, so because the energy in the internal store of the tea decreases, the temperatures decrease until it's the same as the surrounding temperature. But if I have a cup of iced coffee, so initial temperature is 10 degrees, final temperature will be 30 degrees because this is the temperature of the surrounding air. Okay, so because iced coffee was at a lower temperature, therefore notice the arrow, the thermal energy is transferred from surrounding air into the coffee, right? So eventually the iced coffee will be at the same temperature as the surrounding temperature. Okay, so A1, two metal teapots are identical except that one is black on the outside and the other is white on the outside. Okay, initially the teapots are in thermal equilibrium with each other. State what is meant by thermal equilibrium. So let's see how we answer this. Okay, so basically this is the definition that they are looking for. Thermal equilibrium describes a state in which two or more objects have the same temperature, and important to include that there's no net transfer energy between them. Okay, so state why the teapots are initially in thermal equilibrium. They have the same temperature, that's it. Okay, so if I'm not wrong, this was a very old O-level questions, right? Okay, let's move on. Part B, describe in microscopic terms. That means we need to look at the particles or the atoms. Okay, the particles. Okay, how conduction occurs in solid via vibration of atom molecules. So if you recall, last chapter I said vibration is only reserved for solid. For liquid and gas, they are fluids. So you cannot use vibrate. Only vibrate is used for solid particles because they are fixed to their position and they cannot move about. So whenever there's a change in the temperature, surrounding temperature, their Ke will change. Therefore, they can only increase their vibration. If temperature is high, Ke increases, their vibration increases, or the other way around. Okay, so this is the definition that you need to memorize. Conduction is a process of energy transfer where energy is transferred through the passing on of vibrational motion from one particle to another. Okay, now materials that can transfer energy quickly by conduction are good thermal conductors. When you're answering the question, it is important to include the word thermal and not just saying conductor. You must say good thermal conductor because later on in Sec 4 you will learn about electricity, then there will be electrical conductors. Okay, so for the chapter of thermal energy transfer, it is good to include the term thermal. Now, materials that transfer energy slowly by conduction are poor thermal conductors. Okay, we don't use the word bad, just use poor. Okay, or sometimes we refer to them as thermal insulators. Okay, so let's look at conduction in non-metals. Okay, so we are looking at solid non-metals. Okay, so this is the process. I believe this was covered in Sec 2. Now, this is heat source. So when temperature increase, the particles nearest to the heat source will vibrate more vigorously. This is a key term you need to use about their fixed position. Through collision, this is also important term. The energy is transferred from the more energetic particles to the less energetic particles. Therefore, as more energy is transferred from left to right, particles here also begin to vibrate more vigorously. So notice the word vibrate more vigorously, collisions are continuously being used in this explanation. Okay, so this is how we explain how conduction happens. Now for conduction in metals, okay, this is also solid. So besides the vibration of the particles, as you know in chemistry, for metals, they actually have free electrons, right? So in addition to the same process in non-metals, so you need to mention free electrons over here. So when the heat source is applied over here, electrons also increase in their kinetic energy, and therefore they will move more quickly towards the cooler end. Okay, they move easily and quickly to the cooler end and transfer energy to the particles there by collision, right? They collide and transfer their energy, right? So it allows the particles at the cooler end to begin to vibrate more vigorously. Okay, so this is an advantage that metals have over non-metals. Okay. Okay, solids are generally good conductors because particles are packed closer together and they vibrate in their fixed position. So it is very easy for them to pass on the vibration or the energy because they cannot move away. They are in their fixed position, right? Now, compared to solid, conduction through liquid and gases are not as effective because particles in liquid and gases are spaced further apart than those in solid. So it's not easy to find the next particle to collide and transfer the energy. Okay, so example, air trapped in between fibers in a woolen jacket makes it a good insulator. Okay, so that's for conduction. So what kind of questions can they ask for conductions? Let me write it down. Okay, so these are the 4 common questions that they may ask for conduction. Basically, it is the definition of conduction. Now, number 2 is describe process of conduction in solid or in metals. Please remember to include free electrons. Then they will ask you for why is solid the best conductor among the three states. So you must talk about the particles being able to only vibrate about their fixed position. So it's easier for them to pass on the energy by collision. Okay, then they will ask why is metal versus non-metal? Why is metal a better conductor? Then again, you have to bring in free electrons. Okay, so when do we know the question is asking about the process of conduction? When you see things like metals, when you see contact, there must be contact, right? Okay, then now we can go to success criteria C, describe in terms of density changes, how convection occurs in fluid. So now we go to the second process, which is convection. And the key word to think of is density. Okay, now convection is a process of energy transfer by means of a convection currents of a fluid. This is important due to a difference in density. So this is the definition you need to memorize. Okay, so later on I'll tell you the template if you have not attended my Sec 2 class, but I think your other teachers will also talk about it. So my template is actually called VDACC. Okay, and they each stands for something. V stands for volume, D stands for density, A stands for action, C is to compare, and the other C is convection current. Okay, let's see how this is being used. So step 1, the liquid at the bottom of the pot expands due to heating. So you see this is the heat source, right? So the liquid over here, let me use a red color, will be heated, right? So when they are heated, what happens to their volume? Their volume will expand. So this is the V. Okay, now therefore it will become less than. So this is the D. What is the action? It will rise towards the top. So you see this is the movement of the hot liquid. Okay, then now we need to do our comparison. The surrounding cooler liquid, surrounding cooler and denser liquid then sinks to take the place of the rising liquid. Okay, so they'll sink. So now I'm doing a comparison. This process repeats and causes convection current. So this is how we answer, right? Point to take note is sometimes they may give you the medium is nitrogen, which is a gas, or air. Okay, it may not always be liquid. So always adapt and change. So we always talk about if this object is being heated, we always talk about the hotter substances first. How about if it's aircon? Okay, let's say we have aircon at the top of the room. So as you know, the aircon will actually cool the air around it. So they'll become cool air. So when it's cool, what happens to the volume? Remember VDACC, the volume will decrease, right? So density will increase. Why does density increase? Because of density equals to mass over volume. Mass is constant, volume decreases, therefore density increases. Therefore, the action next will be it will sink. So now we do our C, we compare. Okay, the warmer air, okay, take note now we are talking about air. The warmer air will then rise to take the place of the cooler air. Okay, will rise. Okay, so when it rises, then it will also in turn be cooled down. So then this sets up a convection current. Okay, so please use this template to answer. You will not miss any point. Okay, so let's look at this question. C1, when switch on, the filament lamp shown below loses energy by convection. So this question is an O-level question. They already state the process by which how the filament lamp transfer energy to the surrounding. So filament lamp is now hot. Okay, so what happens to the gas around it? Take note, it's nitrogen gas, so you cannot be using air, you cannot be using liquid, right? So the nitrogen, let's use our VDACC. Okay, VDACC. So the V is for volume. The hot nitrogen gas, okay, expands. So this is V. Then the density of the nitrogen gas decreases. Okay, because of density equals to mass over volume, so the action is to rise. So it will rise up, the hot nitrogen gas will rise up, then the cooler nitrogen gas, okay, that is away from the hot metal filament will sink. So we do our comparison. Okay, we talk about the cooler nitrogen gas away from heat source will then sink. Away from the filament, it will sink to take the place of the rising hot nitrogen gas. Then this sets up a convection current. Okay, so it's always using this template VDACC. So we have a freezing compartment, so I'll just talk you through it. Why is it at the top? How is it going to cool all the air in the fridge? So this freezing compartment will cool the air around it, right? So the cool air will contract, the volume decreases. Okay, volume decreases, therefore the density increases, then the action, it will sink. Okay, then the warmer air at the bottom will rise to take the place. So we are doing a comparison now. So we always start from the cause of it, right? We don't talk about the cold, we don't talk about the warmer air at the bottom. We always talk about the one that started it, which is the freezing compartment cooling the air around it. So after we compare, then this will then set up a convection current. So this convection current, the setting up of it is like the conclusion. All right, so with this you can explain for this question. Okay, so for the last process is actually radiation. Okay, so explain that energy transfer by electromagnetic radiation does not require a material medium. So previously for conduction, we mainly focus on solid, be it solid non-metal or solid non-metal. Then for convection, we focus on fluid, right, which is liquid and gas. Why don't we talk about solid in convection? It's because the particles are in fixed position, so they can't actually move. But for the particles in fluid, liquid or gas, they can actually move around. Okay, so for radiation, we don't even need any particles, so it can even occur in vacuum. Okay, let's see. So in both conduction and convection, physical medium, either solid for conduction, for convection is liquid plus gas or gas. Okay, a physical medium is needed. Okay, so radiation is actually the process of energy transfer by EM wave, electromagnetic wave, which you haven't learned. We'll cover very shortly without the aid of a medium. So this is the definition. Please memorize. One point to take note is that the radiation can take place through a vacuum. Vacuum means medium without particles. That means it doesn't even have air particles in it. Alright. Okay, so take note that all objects with a temperature above absolute zero is 0 Kelvin or minus 273 degrees. By the way, 0 Kelvin, okay, 0 Kelvin, okay, it is absolute zero. This is equivalent to negative 273 degrees Celsius. So 1 Kelvin will actually be minus 272 degrees Celsius. So it is a linear change. Okay. Therefore, what happens when I am having 0 degrees? That means it is minus 273. Sorry, it is not minus. It is 273 Kelvin. Okay. It is 273 Kelvin. 100 degrees will then be 373 Kelvin. Okay, so every 1 degree changes is equal to 1 Kelvin change. Change of 1 Kelvin is equal to change of 1 degree Celsius. Okay, so what does radiation depends on then? It depends on the surface color and texture. So this is important and this is a fact. Black and dull matte surfaces are good emitters and good absorbers. White and shiny are actually poor emitter and poor absorber. So whenever we talk about radiation, whether it absorb or emit, we have to first determine if the object is at a higher or lower temperature compared to its surrounding. Okay, I think I did the the example of Egypt in class. So now I'm going to do my dim sum restaurant. So as you know, in dim sum restaurant, let's say I have a teapot. In dim sum restaurant, they actually serve hot tea. They serve hot tea, right? Okay. So if it's hot tea, that means this tea inside this kettle is hot, or teapot is hot, and of course the surrounding will then be colder. So now if I want to serve hot tea to my customers, okay, do I want, and because this is hot and the surrounding is cold, that means the thermal energy will be emitted to the surrounding. The teapot will not be absorbing thermal energy, it will be emitting. Why? Because it is hotter than the surrounding. So if it's hotter than the surrounding and I do want to end up serving hot tea to my customer, I will be using a white teapot. Okay, white teapot, because white is a poor emitter of thermal radiation. Okay, so when I ask you what color teapot should I use, you should reply white, but when you explain, you can only include because white is a poor emitter. Okay, you have to adapt to the context, you have to answer according to the context, right? So it will not absorb thermal energy because the teapot, the content is hotter, so it will not absorb from the colder surrounding, rather it will emit thermal energy to the surrounding. Okay, so let's say now my dim sum restaurant failed, okay, and my friend recommended me to open up a western restaurant. Okay, and for western, selling western food, I'll be serving cold iced lemon tea. Okay, right, nobody wants hot tea in a western restaurant. Yeah, that's for me. So if it's cold, right, then where is it hotter? If it's cold, then iced tea, you know, if this is iced tea, it will be actually colder than surrounding. That means the surrounding, even if I on aircon 24 degrees, it will be hotter than the content inside. Therefore, thermal energy will be absorbed by the kettle, by the teapot. So do I have to change the color of my teapot? No. In fact, I will use back my white teapot, right? Because eventually I want to serve cold tea. I want to serve cold iced tea, right? So do I want my white teapot to absorb thermal energy? No choice, it will absorb thermal energy because the surrounding is actually hotter than its content, so it will still be absorbing. But do I want it to absorb as much? No. Therefore, I use a white teapot, because then white is a poor absorber of thermal energy, thermal radiation, right? So even though I'm serving different kinds of drinks, hot for my dim sum, ice tea for my western food, okay, it really depends on the context. It really depends on whether you want to absorb as much thermal energy or emit as much thermal energy. Okay, so the question to ask yourself is to compare where is it hotter? Is it the surrounding or is it the object itself? Then you ask yourself whether you want to emit or absorb thermal energy. Then you choose your color, and based on whether you want to absorb or emit, then that will be how you frame your answer. Okay, it takes a little bit of getting used to. Okay, but always ask yourself, where is it hotter? Okay, so this is actually covered in here, right? I covered over here. Okay, next thing that actually affects the rate of energy transfer by radiation. Just now we did color and texture. So dull, matte, black, they are good emitter and good absorber. Yeah, that's a fact. Yeah, so another factor that will affect the rate of energy transfer by radiation is the surface temperature. Okay, the larger the temperature difference, okay, between an object surface relative to a surrounding, the higher the rate of emission absorption of thermal energy. So imagine you're standing beside your friend, okay, who didn't run 2.4. So although your friend may not be, yeah, so you will not, maybe you won't feel any, get any thermal radiation from your friend. But imagine now you have a friend who just came back from 2.4 and sweating like crazy, right? So his body temperature will definitely be higher than yours. When you stand near him, so besides the smell, you will also feel his thermal radiation, right? Because the difference in temperature between you and your friend who just ran 2.4, the temperature difference is large. Okay, therefore you will feel some kind of thermal radiation from him. Okay. Now, rate of energy transfer by radiation is also affected by surface area. The greater the surface area, the higher the rate of thermal radiation. Alright, so these are the three factors that affect radiation. And what they like to ask always is, can radiation happen in vacuum? Of course, but radiation cannot happen in convection and radiation. Convection and conduction. Sorry, what am I talking? Conduction and convection cannot happen in vacuum. Alright. Okay, so this is a summary for the three factors. If I have lower surface temperature, smaller surface area, and smooth, shiny, and light colored surface, then the rate of absorption or emission will be slow. When will it emit? When will it absorb? Then you have to ask yourself, where is it cooler? Where is it hotter? Okay. That means, on the other hand, if I have higher surface temperature, larger surface area, or matte, rough, and dark colored surface, then there will be a higher or faster rate of emission or absorption. Whether it emit or absorb, it depends on the surrounding temperature, whether you are hotter or you are cooler than the surrounding. Okay. So let's look at one example. D1, two metal teapots are identical. One is black on the outside and the other one is white. So when will you know it's radiation? When they talk about color, when they talk about surface. So black, it is a good absorber and emitter. Okay. So white will be poor. Okay. They are filled with the same amount of boiling water. So ask yourself, where is it hotter? It is hotter inside. It is going to emit thermal energy. So later on, I cannot talk about absorption because the surrounding is actually cooler. The surrounding cooler. So thermal energy always flows from a region of higher temperature to a region of lower temperature. And they are cooling down. That means they are both emitting thermal energy. Now, which teapot will cool down more quickly? The black one. Okay, because black teapot is a good emitter of thermal radiation. You cannot talk about absorption here. If you talk about absorption, marks will be deducted. Alright. So please read through by yourself some of the real life application of the concepts of conduction, convection, and radiation. Okay, I will not go through with you. You just read through by yourself. If there are any questions, you can ask me. Okay, so this is the theory part of thermal processes. All right, I will then do another video on the remaining questions. Okay, so before you watch I'll be doing video for E2 and E3. Okay, so before you watch the video, please attempt this question and see that you are actually comfortable with using the template, like example VDACC or black color, all these things, that you are comfortable in answering the questions. All right, see you in the next video.